Okay, so question 7 on worksheet 1. So in your notes, the back of your notes, you had a question that had multiple vectors, like number 8 is about an airplane. Question 7 is not about an airplane, but the work behind it should be exactly the same, though. Same logic, all that kind of stuff. So, again, I know I went over that back page of notes with you last time, but since that's the hardest part and also the most useful part, kind of the point of us even doing this, it makes sense to be sure that you're very, very good with this. So you should have already tried this one, and you should have already tried looking up my solutions online and learning from your mistakes. But I still think even if you got the right answer, or you got the right answer after you saw my work, or whoever's work was, that's not my solutions. It's still a benefit you to go over it again. All right, so for this particular question, I would understand maybe why you try to sketch the picture like this. But let me tell you why I don't like it and show you what I would recommend instead. Okay, so you've got an object. So I'm going to say my object is right here at the origin. And you're pulling on the object with 800 newtons at 60 degrees. So newtons is just a way to measure how much force you have. So 60 degrees, I'm pulling on it half strong. But I've got a second force at negative 15 that's pulling on it at 650 newtons. Okay, so I can see why you would maybe sketch the picture this way, because here's your object. You've got two things pulling on it. That's what it would look like in the real world, if you will. But this doesn't really help you see the resultant vector, and it doesn't help you make sense of why you want the component forms of these and why you would add the component forms of these. So it's not that this is wrong, I just don't think that that's a good strategy to use long term. Instead, what I would recommend for you is make one of these vector 1. It does not matter. I'll stick with this being vector 1. Sketch it. And then start the second vector at the end of the first vector. So make another xy and say the second vector is negative 15, 650. And if this is 800, 650 would look something like this. Of course, we'll need some angles to make sense of patterns. The reason why it tends, I don't know, maybe it's just me, but it seems like over the years this is what helps you make sense. Because you can see that you started here. If you just had this force, you would land here, but you also have this force, so you end up landing here. So this would be the actual path. And this lets us visualize the resultant vector, which is the result of both of those vectors happening. So what I can say quickly is that this vector pulls it right and up, and this vector pulls it right and down. But to know exactly what happens in the end of all this, I need to know how much is this rock pulling right and up, and how much is this pulling right and down. So that's why I care about the component form. Component form lets me be able to figure out how much left to right, how much up or down. How much left to right, how much up or down. Because then it's easy to work with. Alright, so our trigonometric form that we did last time, I usually skip straight to the arrow notation because it's really just distribute. I like the arrows better than I and J, but I'll write it in one time for you. You can say 800 times the cosine of this angle I plus the sine of the same angle J. But if you distribute that 800, you get 800 cosine of 60I plus 800 sine of 60J. And again, I just prefer the arrow notation instead of I's and J's, but it doesn't matter. Alright, so I guess if I want to, and I can practice and look at the decimal, practice and look at the decimal. So what this represents is how much this vector is pulling to the right, and how much this vector is pulling up. So I'll try to color this to help you see that. That's why I care about component form. Okay, I'm going to do the same thing with this guy. Component form of him, going right and down. And how much I pull to the right would be 650 cosine of that angle from the positive x-axis. 650, sine of that angle from the positive x-axis. Again, you can start in trig form if you want to. Distributing the 650, putting in arrows, and removing the hypotenuse. Just like a little this. So let me break these numbers down super basic for you, because I know these numbers, sometimes people get bogged down in the numbers and all the decimals and all that kind of stuff. Let's say that this length is 3. Okay? If this length is going right 3, and this length is going right 2, how far to the right is this one going? This one's 3, this one's 2, this one would be, right, you add them together, right? Let's say this one's going up 5, and this one is down 1. What does that mean for this? You're just adding them together, right? You're taking how much this goes to the right, plus how much this goes to the right. So you're adding these guys together. So you add the horizontal components to get the horizontal component. And you add the vertical components to get the vertical component. Okay, so take note of the horizontal component only has cosines in it, and the vertical component only has sines in it. Just like with a circle, cosine helps us determine the x values, sine helps us determine the y values. And so, sure, I could type those in, I could get a number, I could round it if I wanted to, but I'm going around just yet. But this is how far left or right it goes. I'm going to call this x. I'm actually going to store it in my calculator as x. It's this. This is how much up or down my resultant vector is going. I'm going to type that in and store it as y. That represents that. And at the end of the day, I end up knowing 2 of 3 sides of a right triangle. So I can find things like what is the hypotenuse and what is the angle, which directly impact what we care about for this question. So I'm going to store these as x and y. So if I want Pythagorean theorem to find the hypotenuse length, the hypotenuse will be the square root of the length squared plus the leg squared. And since I'm going to store x and y in my calculator, I'm going to type it in my calculator like that. And if I want to know the angle, and I know opposite and adjacent, that would be tangent, but it's an angle. So y over x, I'm going to ask my calculator that. And then based on the range of inverse tangent, I might need to add 180 degrees to that, maybe not. Since it's in quadrant 1, I know that it's not. If you don't remember those rules, I will show you a way around that for this year. Okay, so there's really how far it's going to the right. I'll store that in as x. This is how much is going down. So that's y. Now you're still going to always add your vectors together. You don't have to worry about subtracting because one goes down. Because the trig is smart enough to know at 60 degrees, sine is positive, so that part's going up. But at negative 15, sine is negative, so it will automatically subtract for you. You just add your vectors together. Alright, so here's my horizontal component x, here's my vertical component y. Pythagorean theorem. Left squared plus leg squared, take the square root of that, and that's where you get the overall force. It was measured in newtons, so it stays in newtons. And inverse tangent of opposite over adjacent is about 27 degrees. So does this angle look like it's 27 degrees? Right, that's in quadrant 1. So it would not make sense to add 180 there. You know, they add 180 if it was pointed in the wrong direction. So it had nothing to do with the airplane, but I still found component form of both vectors. So I added the vectors together to get component form of my resultant vector. And what component form of the resultant vector means is how far right or left is it going, how far up or down is it going, which ends up being two sides of a right triangle. The diagonal theorem finds the third side, which in this case represents the magnitude of my resultant vector, which is the total force being used. And inverse tangent of y over x gives me the angle that it's being pulled at. So I know exactly how hard and which way it's going. Okay, so from that one that you tried for your homework, you okay with that? With all questions you need to ask, we'll move on.